Okay.
Okay, everybody, welcome to the Global Non-Commutative Geometry Seminar. Today, we're happy to have Dr. Yongle Jiang, from Dalian University of Technology, give us today's lecture. He will talk about some results on continuous orbit equivalence rigidity. Let's welcome.
Okay. Thank you for the introduction of Professor Wang, and thank you for the invitation of Professor Yao. Today I'll talk about continuous orbit equivalence rigidity. It's not also related to the non-commutative geometry, but I would introduce some geometry in this talk. Let's see. This is the brief outline for my talk. I have to say that part of this talk is based on joint work with my academic brother, Nanfu Chong, who is in South Korea now. Let's see the convention in my talk. I would always use G and H to denote countably infinite discrete groups. And Gx on X is a continuous action on a complete Hausdorff space X. And we already assume this action is topologically free. This means that for any non-identity element G, the non-fixed point is dense in this space X. A general question we want to understand is to classify this action up to certain equivalent relation. Of course, in this talk, I would mainly focus on conjugacy and continuous orbit equivalence, these two relations. A point I want to mention is many questions and theorems in this talk have counterparts in the Maribor setting. This means that in the Maribor setting, we also have some probability merit preserving actions, and many theorems also works in that setting. And in fact, I would emphasize on these analogs. Let's first review the definition of this conjugacy and continuous orbit equivalence. So we are given two topologically free actions, Gx on X and Hx on Y. Okay, let's first see the conjugacy relation. So this means that you have a group isomorphism phi and a homeomorphism theta, such that the theta Gx equals phi G X on this theta X. This just means that you have the commuting diagram. On the left side, you have this G action, and on the right side, you have the H action. And this diagram commutes exactly means this identity holds for any X in X and any G in G. And another relation is the continuous orbit equivalence. It briefly means that you have a homeomorphism theta from X to Y, which identifies the G orbits with the corresponding H orbits in a continuous way. So let's see, you have this G orbit Gx, and after you apply this homeomorphism theta, you get this H orbit of this theta X. And since we have this identity, if you take any element G in this group G, then you get some element in this H. Let's denote this element by C, G, X. In this definition, we require this map C defined in this way is continuous. And for the reverse direction, we also have the C prime map, and we also require this map is continuous. If you think for a second, it's clear that conjugacy implies continuous orbital equivalence. But conversely, continuous orbital equivalence does not imply conjugacy in general. This is not a so easy example to illustrate this non-implication. But if we allow this group and this space to be finite for a moment, then you can consider taking any two finite groups with the equal cardinality but not isomorphism. Then you can consider Gx on G by left translation, or just means left multiplication by the group operation. And then you can also consider Hx on H itself by left multiplication. Since these two group has equal cardinality, then this map Okay, then these two actions are continuous orbital equivalence because these actions are transitive actions. And if you assume these two groups are not isomorphism, then they are of course not conjugate. So this is a simple example to show that continuous orbital equivalence does not imply conjugacy in general. But of course, for this example, it's a finite groups X on a finite space. And if you want to consider these compact spaces, which are not finite, which are infinite, you have to have more complicated constructions. But we will see one in the end of this talk. Another thing to say is that historically speaking, this notion have been introduced before Xin Li write down the definition in here. In general, or history speaking, so Boyer, Giordano, Matsumoto, and other people, they have studied this notion for Z actions, and mainly on the contour set. And their motivation to study them is just to consider the classification of system algebras from the group actions. Xin Li initiated the study for continuous orbital equivalence for general group action in 2015. So I use COE to denote the continuous orbital equivalence. Another thing to say is that lots of work has been done in the Marable setting. For this, I mean, if you consider these definitions, but you consider them for PMP action, probability matter preserving actions, you can also define conjugacy and also define the so-called orbital equivalence. So this means that you have an isomorphism between the two mirror spaces, and you have this group isomorphism, then you define conjugacy. And this equality holds for almost every X and for all G. For orbital equivalence, it means you have a measurable isomorphism from X to Y. And also this equality holds almost everywhere instead of everywhere. So this is the so-called orbital equivalence relation. And there are also a lot of famous work doing something on this orbital equivalence relation, mainly on the rigidity part. And we also, I think we have learned something like the famous Dye theorem and Austin-Weiss theorem, and the Zimmer's theorem, and Furman, Gabriel, and so on. And besides that, we can also define some related notions. For example, in the definition of this orbital equivalent relations, you can consider something more stronger conditions. For example, in general, for the orbital equivalent relations, you have some measurable map C, but you can put more assumptions on the C to define the so-called integral orbital equivalence. This means that the C is an integral map, and also the so-called LP orbital equivalence relations. In this case, the C is just an LP map, and also something more general, the so-called Shannon orbital equivalence or memory equivalence. But now in this talk, I will mainly focus on this topological setting for the continuous orbital equivalence defined in this way. For the definition, there is something you can observe. For example, since we assume these two actions are topologically free, you can verify that these maps defined in that slide, C and C prime, are cocycles. So this means that they are continuous maps satisfying the so-called cocycle identity. The cocycle identity is written here. It's just C G1 G2, comma X equals C1, C G1, comma G2X, C G2X. And for trivial actions, this simply just means you have a continuous map. We satisfy the group homomorphism relation from G to H. In general, we call these maps C and C prime as the orbital cocycles. In the macro setting, they are usually called the so-called Zimmer cocycles. Clearly, if you take any group homomorphism from G to H, denoted by phi, And you can define a continuous cocycle easily in this way. Then the question we really want to consider in this talk is, when does this continuous orbital equivalence imply conjugacy? So this means when you can really have a reverse direction in this implication. 2 implies 1 when it happens. Let's give some name. So if you have a g x on x given, and if the second action is unknown in general, then suppose 2 implies 1. When it happens, we will say that this first action g x on x is the continuous orbital equivalent rigid actions. So this means that if you know g x on x, and you know it's continuous orbital equivalent to some mysterious action g x on h x on y, then you can deduce their conjugate automatically. And in the member setting, mostly related to this talk, we have this so-called Popa's famous orbital equivalence superrigidity theorem. Let's review this theorem. So Popa proved that suppose you take a G which has property T and contains no non-trivial finite normal subgroups. The simplest case would be you take this G equals P SLNZ. So it means that you use SLNZ module out of the center. SLNZ just means the group consisting of all n by n matrices with determinant 1 and entries from Z, from these integers. And since we want to have property T, we just assume this n is no less than 3. And if you consider the Bernoulli shift, Popa proved that this action is the orbital equivalent to superrigid actions. So this means that if you have orbital equivalence between this Bernoulli shift and any other free ergodic PMP actions, then they must be membrane conjugate. This is the landmark remark. This is landmark result in this orbital equivalence rigidity theory. Here are some remarks. First, by this famous Austin-White theorem, we know that any 2 non-atomic PMP ergodic actions of any infinite amenable groups are orbital equivalents. So this means that if you want to have orbital equivalent superrigidity, the acting groups must be non-amenable. So it only happens for non-amenable group actions. And this theorem has motivated a lot of research. For example, people have studied whether we have a more general group satisfy this orbital equivalent superrigid action, superrigid theorems. For example, we now know that if G is a product of 2 non-amenable groups, or just 1 amenable groups with another non-amenable groups, suppose they are both infinite groups, then this also happens. And there's more groups satisfying this theorem. And also people also study whether we have more actions other than Bernoulli shifts to have this property. This is also known. There's many works motivated by this landmark results. Another thing to say that this theorem is very strong in the sense that, at least from my point of view, it's very special in the sense that first, till now, I don't know, or we don't know any other proofs without using the deformation property of these Bernoulli shift actions. We don't know other new proofs. It essentially relies on Popa's argument. The second thing is that for people studying non-amenable group actions, this is the only ingredient we can use to construct quotients of Bernoulli shifts which are not membrably conjugate to Bernoulli shifts itself. So this is the ingredient to construct such quotient actions. I think we don't know other ways how to construct non-Bernoulli quotient actions of a Bernoulli shift. Let's say some words on why we study this continuous orbital equivalence. The main motivation comes from the connection between continuous orbital equivalence and system algebras. So we know that given you, suppose we are given a continuous action gx on x, we can construct this so-called cross-product system algebra. And one can observe that if you have two actions, suppose these two actions are conjugate, then automatically they are continuous orbit equivalence, which in turn implies those two cross-product constructed isomorphism as system algebras. A classical, I should say, a recent result, or maybe people have know this result before, but but no one write it down. So Xin Li proved that for any two topologically free actions, the following two statements are equivalence. One is that these two actions are continuous orbit equivalence. The second one is that these two cross-product are isomorphism. Isomorphism where some phi, such that phi also identifies these two algebra Cx and Cx and Cy. So this means at least theoretically speaking, we can have some tools to study this continuous orbit equivalence by studying these system isomorphisms. And why we are interested in this, because at least in the Marlborough setting, we have some similar implications, and it's now a hot topic to study when you can reverse these directions. So perhaps perhaps we can do the similar thing for this topological setting. We can ask whether we can just reverse these directions. So when do you have this? When do you have this implication from this isomorphism of system algebra to the conjugacy? I don't know any result along these directions in general. And another thing to say that this equivalence has been known, is known in the Marlborough setting quite a long time ago. It was due to an observation of Singer in 1955. Now in this Marlborough setting, so it's for isomorphism cross products from algebras and orbit equivalence thing. Now let's briefly say how do we prove this continuous? How do we prove this continuous orbit equivalence rigidity? So roughly speaking, it means you only need to show these orbit cocycles are trivial in certain sense. But what are trivial cocycles? Trivial cocycles are defined in this way. So suppose we are given two continuous cocycles, C1 and C2. First, we can define some equivalence between two cocycles in this way. So if C1 can be written as C2 twisted by certain terms on the left and on the right in this way, then we say that two cocycles are equivalence. It's easy to check that. Suppose C2 is a cocycle. You define a map using the right-hand side. It's automatically a cocycle. And this map T, here we require is continuous because we are talking about this topological setting. So every map is assumed to be continuous. This map T is called the transfer map. And we say a cocycle C is a trivial if it is equivalence to a homomorphism phi. Recall that we have defined a cocycle using a homomorphism before. So if you have a homomorphism phi, you can define a cocycle C prime from G cross X to H by mapping Gx to phi G. So you forget about the second coordinates. You get a cocycle easily. And if C is equivalent to this phi, then we call C is trivial. The main tool used to prove this continuous orbit equivalent rigidity is the proposition of Xin Li. Let's see this proposition. So you have suppose you have a continuous orbit equivalence between two actions. I denote this homomorphism from X to Y by phi, which witness this continuous orbit equivalence. And suppose we know the orbit cocycle C is equivalent to a group isomorphism from G to H via transfer map T. Then one can check. You can modify the homomorphism phi in this way to get a map theta and this theta would intertrain these two actions. So this means that you will have some commutative diagram using this theta instead of this phi. The commutative diagram is the one defined in this is the one used to define conjugacy. Furthermore, if you know G is torsion-free and amenable, then you don't need to know rho is the isomorphism. You only need to know rho is a homomorphism. To get some feeling about this proposition, how it works, let's simply check. If you define theta in this way, it indeed gives us an equivariant map between these two actions. So we don't prove this this injective part of homomorphism or the onto part. We just check this equivariant part. So let's see how do you check this. So if you have an x from this space, if you apply g to it, you get a gx. If you apply theta to it, you get a point in the second space y, and this is the theta x. If you want to check, this diagram commutes. So this means that you at this place you have to check if you get this one from this arrow or from this arrow, this will match up. So this means that I have to check this theta gx going down first and then go right is equal to this rho g x on this theta x. So go right first and then go down. You write down the definitions. Theta gx means you get this tgx inverse x on phi gx, and rho g theta x means you apply rho g to this term. Since these two elements from the groups, so you can combine them together. Write it as rho g tx inverse 1. You want to check these two terms are equal. This indeed holds because if you recall the definition of this phi and the assumption C is equivalent to rho while this transform map T, you will see that since phi is the orbit phi gives the continuous orbit equivalence, so phi gx equals cgx x on phi x. But cgx is assumed to be this tgx rho g tx inverse. This is the definition of the C equivalent to rho while this T. So we do have the one inequality. This one equals this one. Then you can just move this term to the left-hand side. You will get this tgx inverse 1, x on phi gx equals the rest terms. So it's rho gtx inverse 1, x on phi x. So indeed, this equality holds here. So to sum up, to show continuous orbit equivalence implied conjugacy, the main task is to untwist the cocycle. This means that you want to show these orbit cocycles are trivial in this sense. So you have to construct this rho and to show it's equivalent to this rho. And if you know the orbit equivalence theory, you know that this criterion is known in the orbit equivalence setting. Now let's talk about some non-continuous orbit equivalent rigid results. So for the following actions gx on x, I will show you. It satisfies this condition. So it satisfies that if this action is continuous orbit equivalent to another action h x on y, we usually assume these actions are topological free. Then they are automatically conjugate. So which actions we have for this gx on x? We have several actions. So first, the result is due to Klaus-Schmidt. He proves that if you have this G to be this ZD, D is bigger than or equal to 2, and you consider these four shift actions. Here is a finite set. Then this action satisfies this result. So it's continuous orbit equivalence rigid action. If you have this action is continuous orbit equivalent to hx on y, then these two actions are conjugate. After that, you have this Boyer-Tomiyama result. Now you take any topologically free and topologically transitive action, Zx on X. But now you have to assume the second group is the same, is also integer groups. Then suppose you have Zx on X is continuous or equivalent to Zx on Y. Then these two actions are conjugate. Xinli also put some generalizations of this first result. He showed that for more general class of groups G, and you allow this bottom space X0 to be compact instead of finite here. Then you can also have some continuous, this action is also continuous orbit rigid action. He can also deal with some subshifts instead of these full shifts. Together with Chong, we have put a more general result. And this in our original result, we have more assumptions on this G. We have to assume it is not only finite generating with one end, but also not torsion. So it contains at least one element with infinite order. Shortly after our result appeared, Dave Bruce-Cohn, who was a postdoc in Chicago at that time, he can just remove the assumption that G contains at least one element with infinite order. And so combining these two results, we can say that we have more general result written in this way. Let's explain this result. So we still have considered these full shift actions. But now G can be any finite generating group with one end. Here, one end is a notion, a basic notion in geometry group theory. It can be simply explained in this way. So if you have a finite generating group, you can consider its Cayley graph. Then in the Cayley graph, if you remove larger and larger balls from it, and then you look at the rest of part and count how many infinite kinetic components you have. If you enlarge the balls, if you enlarge the radius of the ball you remove, then you count the limit of this number of infinite kinetic components in the rest part. Suppose, and it's known this limit can only take the values 0, 1, 2, and infinity. If it is 0, it's equivalent to say G is a finite group. If it equals 2, it's a theorem saying that this G must be virtually cyclic. So it has a finite index subgroup, which is cyclic. And here cyclic really means infinite cyclic. And if you have infinite ends, so I mean the limit equals infinite, then it simply means that this group G looks very similar with a free group. I think people are familiar with this. The Cayley graph of the free groups is like a tree. If you remove more and more vertices, and I mean, if you remove larger and larger balls and remove more and more vertices, you will get more and more infinite kinetic components in the rest of part. So this limit is equals to infinity in this case. But if G equals Z, you can think of Z as a line. So if you remove a finite part from this line, so I mean, for a finite part, it means say you remove negative n to n this interval, you get two infinite components. And so the Z intergroup Z has two n's. But if you consider G equals Z2 or Z3, so on, you will see that it has only one end. And it's a known fact that if G is not virtually cyclic, but G is amenable, then it is automatically just one end. So it always has one end. If G is infinite and has property T, it's also one end. And if G is a product of two groups, which both are infinite, then this group G has one end. So in particular, this theorem generalizes this Schmidt's result, also this part, the result in this part, the result seen in this part. And of course, you can see the similarity between this result with Popa's orbit equivalent superrigidity result. It's really just a topological version of Popa's orbit equivalence super rigid result. And after this result, I also generalize it further to co-induced actions. It's a notion I will not explain here, but I would say that this result generalize the last result further. However, there is some defect in these two results. The thing is that it doesn't apply to minimal actions. If you consider the flow shapes, it always contains fixed points, so it's never a minimal action. But for people studying system algebra, they are mainly interested in simple system algebras. So this means that usually they assume these actions are minimal. You can see that from this list, only the secondary result, Boyer-Tomiyama's result, can be applied to minimal actions. For all other results, it contains fixed point, so they are not minimal actions. Related to continuous orbit equivalent rigidity, there is also another result proved by Martinez in 2016. They show that if you consider two minimal equal continuous ZD actions, continuous orbit equivalence also implies some weaker sense of conjugacy, which they defined in their paper and called it to be just the virtually piecewise conjugacy. I will not define it here, but this is a weaker notion of conjugacy. And this result is also a topological version of the famous Ivana's result in the orbit equivalence setting. So Ivana proved a similar result, but in the Maribor setting earlier than this result. So there's still an analog between these two settings. Okay, so let's ask a specific question I want to answer in this talk. So do we have continuous orbit equivalence rigidity for infinite virtually cyclic group actions? Extending the last Boyer and Tomiyama's result, recall that they proved a result for these Z actions. Now I deal with another group. It's a virtually cyclic group, the so-called infinite dihedral group. It's defined in this way. In the algebra class, we have learned some finite versions of this group. This is the so-called 2n dihedral group, the symmetry group about the n polygon, regular n polygon. Yeah, you have rotation. So okay, S means just rotation, and T just means reflection. But now we just consider the infinite version of this group, the so-called infinite dihedral group. Okay, so for this group, we consider any two minimal actions on a compact host of infinite space X. Then continuous, if these two actions are continuous orbit equivalent, then they automatically just conjugate. Here I just put parentheses here because you can check if an action of this group is minimal on a compact host of infinite space, it's automatically topologically free. But on the negative side, we can also construct some non-trivial finite group F, such that if you consider Z cross F, you can indeed find two minimal free continuous orbit equivalent actions, but they are not conjugate. So this means that if you consider this question for infinite virtual cyclic groups, you can have both positive result and negative result. In the rest of the time, I would briefly explain the main ideas behind this proof. First, let's recall some useful notation and observation. So I denote D infinity as an infinite dihedral group. So this you have this generator S for this copy Z, and the generator T for this copy 0 to Z. So T is a reflection, so it has order 2. And T acts on S by mapping S to S inverse. So T T inverse equals S inverse. The picture to think about this group, the picture you want to put in your mind is you think of this group as an infinite two-leg ladder. So on the bottom, you have this subgroup Z. So it looks like a line. On the top, you have the coset space for this subgroup. Since it has index 2, so you don't need to distinguish the left coset or right coset. So, and from the bottom one to the top one, you can have this map T. So this arrow, if I put G on this arrow, it means that I just take the right multiplication by G. You can match up these two lines. So you can think of this as the bottom ladder, bottom leg, and this is the top leg, and this is an infinite two-leg ladder. And if you take S to be this subset, S plus minus 1 and T, and this is a generating set for this group, then this group admits a radial invariant word metric defined in this way. So it briefly means, suppose you want to if you want to measure the distance between this element and this element, it's just a distance 2, because you can go in this way, and this is the shortest path connecting these two vertices. And if you want to measure the distance between this one element and this one, the distance is just 3. You can go in this way or go this way. For those who are familiar with geometry group theory, you know quickly that this is nothing but roughly speaking, it's nothing but the kilograph of this group. But I just don't put all the arrows. I don't put the inverse arrows here. And I also don't put inverse arrows here. So it's really just the kilograph. Okay, so our goal is to show the orbital cycle is trivial in this sense, in the sense of the proposition proved by Xin Li. So I take a minimal action d infinity x on x, and another minimal action d infinity x on a space y. Without loss of generality, you can assume these two spaces are equal. And I denote this C to be the orbital cycle coming from the continuous orbit equivalence between these two actions. Our goal is to show there exists some group isomorphism rho of this group d infinity, such that C is equivalent to this cocycle rho. Be careful that since this d infinity group, this group d infinity contains torsion elements T, so you really need to show this rho is an automorphism rather than a homomorphism. The starting point is you fix any element x in this space, and then you get a map from d infinity to d infinity by fixing this second coordinate. So you can think of this as a map between two ladders with two legs. The first step is also the key step, is to show that for each x in X, you have a dichotomy in this sense. Let's explain it using the picture. It really just means the bottom leg. Recall that the bottom leg just denotes the subgroup Z with generated S. So if you let n change, this Sn just means the vertices in the bottom leg. So this dichotomy just means this bottom leg in the first ladder is mapped to the second one, perhaps in the reverse order, because it can be just Sn or just S inverse n in the second ladder, up to shifting by a finite distance, because you have such a finite distance. So this bottom leg in the first ladder is mapped to the bottom leg in the second ladder up to a certain distance, or just perhaps in reverse order. Since we have this dichotomy, we can use them to define two subsets of this space X, denoted by X sub plus X, X sub minus. Just collect all the elements satisfying one of this dichotomy. You can check these two subsets are both closed and open in this X. So you have really adjust the partition of this X, closed open partition. Now, by the definition of these two subsets, all the distance here is uniformly bounded. So you can just define a map to measure the defect. So let's look at it here. So if X belongs to X plus, then C Sn X is lies in the bounded distance from Sn. So you just multiply this piece by S inverse n, so you get the defect. I denoted by A, Sn X. Do similar thing for the second piece. You can check this A enjoys very good property. It's just a cocycle. Since C is continuous, you can also check A is also continuous. The more important thing is A takes finite value, because by the definition, the distance is uniformly bounded. So the defect just takes finite values. Hence, this A takes finite values. But the better thing for this map A is the range of this A belongs to D infinity instead of this Z. But this is easy. You can easily handle this. So you just define another map D, and twist A by this D. You get an equivalent cocycle A prime. Then A prime also takes finite values, because the map D takes finite values and A takes finite values. The good thing about this A prime is it takes values in the subset, the subgroup Z, instead of this whole group. So you really get a continuous cocycle with finite range, and the range is contained in subgroup Z. But why do I do this? Because I want to use a famous theorem. So let's just review what we have did. We starting from an orbit cocycle C, we construct a defect cocycle A, and we twist A by certain map D to get an equivalent cocycle A prime. Both A and A prime takes finite values, but A prime, the range of A prime is contained in the subgroup Z. Okay, this is what we have now. Next step, since we assume D infinity, the action of D infinity is minimal. Since Z has finite index 2 in this subgroup, in this group D infinity, then you can check the number of minimal Z components is either 1 or 2. So we can split the proof into two cases. The first case is this original action, G just means D infinity. This original action has only one minimal Z components. The second case, it has two minimal Z components. So for the first case, it really just means this subgroup action is also minimal. Now we can use this classical theorem due to Gauss-Chalk and Hedeland in topological dynamics. It says that for any minimal action, if you have a continuous cocycle C taking finite range, and it takes value in this real numbers, there is automatically a coboundary. A coboundary just means a cocycle equivalent to the trivial the cocycle defined by mapping Z to 0 here. Yes. Okay, so it's a very special cocycle. Then we can apply this theorem to this cocycle A prime we have constructed here. because Z lies in Z can be treated as a subset of this R, and you can check. You can really apply it to A prime. So we deduce A prime is a co-boundary. So it's not just a cocycle, it's a co-boundary. And then we use it, we trace back to get some information on C. You can check the C now is cohomologous to the identity map from Z to Z. Okay, so we really have some non-trivial information about C. At the beginning, we only know C is an orbit cocycle. But now we know if you restrict C on the subgroup Z, it's cohomologous to the identity map from Z to Z. In fact, you can do something more. Since you have a reflection T mapping S to S inverse, so you just swap these two leg in these two leg ladders. You can show the C, this original C defined for D infinity, is cohomologous to a group isomorphism rho of this acting group D infinity, and rho is written in this form. In fact, this procedure is well known or classical because it's a general principle, at least in the member setting, saying that if you can untwist a cocycle on a subgroup, then this untwisting also happens in the normalizer of the subgroup. Since the subgroup Z is normal, so its normalizer is just the whole group D infinity. So you can just enlarge the subgroup to the whole group. For second case, so you assume this subgroup action is not minimal. Then you have a similar situation, but more involved. I will not discuss it here. So in this way, you can finish the proof of the rigidity part. For the non-rigidity part, recall that we want to construct certain finite group F such that the product group admits two continuous orbit equivalent actions which are not conjugate. The main idea is to do the following. Suppose you have two cocycles C and C prime for some action, some minimal action Zx on X, taking values in a finite group F. Both this action and this F are to be constructed. Suppose you have two cocycles, then you can just do the well-known scale product actions to get a new action, two new actions. Using cocycle C, you can build up a new action denoted by alpha tilde. If you use C prime, you get another action alpha prime tilde. The observation is the two actions are continuous orbitally equivalent all the time, independent for the relation between C and C prime. So given any two continuous cocycles C and C prime, defined in this way, these two actions are continuous orbitally equivalent. Roughly speaking, it really just means the generalization of the group translation, finite group translation actions I explained at the beginning. So I explained that if you have two finite groups, G and H, with equal cardinality, then you consider left group modification, Gx on G and H on H. They are always continuous orbit equivalent. You generalize this idea to this infinite group actions. You can also have similar thing here. They are always continuous orbit equivalent. But you can show that if they are conjugate, then there's some requirement for these cocycles. Roughly speaking, these two cocycles has to be equivalent. So you know how to achieve this goal. You just construct one action, good action, and good cocycles, such that these two cocycles are not equivalent. So you know you can construct two actions which are continuous orbit equivalent. Since they are not equivalent, you know they are not conjugate. The two actions are not conjugate. In this way, you construct two actions of this group, which are continuous orbit equivalent, but not conjugate. I leave some open questions here, which are natural in this continuous orbit equivalence theory. Since I have no time, I will stop here. Thank you for your attention.
Okay, thank you, Yongle. Why the infinite dihedral group is special? Okay, does the results apply for a little more general groups?
I haven't considered more general groups other than virtual secret groups. What I can say is that this proof is can be considered as a proof, a generalization of the proof of Boyer-Tomiyama, since they deal with the actions. I just go one step further. I consider this the infinity. I can show this theorem. I believe beyond virtual secret groups, we don't have a more general theorem. I mean, suppose G is not virtual cyclic. I don't think any two minimal action, any two continuous orbit equivalent to actions of this group implies they are conjugate. So this means that for the first question here, I don't really think this class G can be large. It should be very small. Perhaps only suppose G belongs to this class G. I don't know, but I think maybe G has to be virtual cyclic.
Okay. Okay. Any questions from the audience?侯成俊，没问题。康李康，people。李康, please ask a question. Any question from the audience?
Okay, I may have a question. Okay, okay. Can you hear me?
Yes, please ask.
Okay, so I think for a large part of the audience, people are not so familiar with the notion of minimal actions, etc. So can you give us some examples that it describes the situation that you mentioned in your theory? I mean, the dihedral group acting on a compact path of space, which is minimal.
Okay. If the dihedral groups is
Yes.
which is residual finite, given any residual finite groups, I think you can construct the so-called odometer actions or called perfinite actions. It is minimal. Or you can say that given any continuous action of this group, you can take a minimal component and you restrict this action on this minimal component, and you get a minimal action.
No. My question is more elementary than this. I mean, just can you give us some natural examples of an action of this group on certain compact Hausdorff infinite space, which comes from analysis or geometry? Or
let me think. Okay. For me, the most natural action is the perfinite action. And if you want a natural action from analysis or geometry,
yeah, so in general, my question is, we are talking about some sort of classification results concerning these group actions, certain actions of these groups, right?
Yes.
And so if the examples that you have about these actions are actually the group acting on a topological space constructing from the group itself.
Mm-hmm. Mm-hmm.
I mean, it's how to say, how to put it this way. So personally, I would rather like to see a natural example that this group acting on certain function spaces or some manifolds, etc. And then the theorem applies to give us sort of
Okay.
some consequences.
One thing I forgot to mention is that if you consider the definition of continuous orbit equivalence.
Yes.
Okay, if you allow this space to be connected, then this is trivial. It becomes trivial because you see, both groups are countably discrete,
Yes.
and these maps are assumed to be continuous. So if X is connected, then the image must be just 1 point. If you fix this G, the image of this map from X to H, it must be connected space, connected set because it's continuous.
Okay.
The image continues connected is connected. So in this case, it's trivial. So in this, so it's for continuous orbit equivalence, it's really just a non-trivial for only say totally disconnected spaces. If you want the space to be manifold thing, then continuous orbit equivalence it becomes trivial thing.
Okay. Thank you.
Any more questions from the audience? Are there any cohomology? 没有话筒，不能说话。OK. Are there any cohomology theories corresponding to the notion of co-cycles in this talk?
No, in general, you don't have cohomology theory because for the target group, if it is not abelian, you don't even have a cohomology group because you multiply these two cocycles. It's no longer a cocycle.
Sorry, say it again.
I mean, if you want to define a cohomology group, usually you have to assume the target group to be abelian. Then you get a group.
I see. Right. So basically, there is no such cohomology theory. Okay. I see. Any more questions? Now, if no question, maybe we can let's thank Yongle again. It's very wonderful. Yeah. Okay, thank you.
Thank you. And just